Hello everybody. Today we're going to be going over Unit 4.2, Linear Relations. When a scuba diver goes underwater, the weight of the water exerts pressure on the diver. So here we are giving both a table and a graph that are showing the relationship between the depth of the diver and the pressure the diver feels. And in the graph, we also have it here, the depth and the pressure. And we're asked, what patterns do you see in the table and in the graph? Okay. So when we look at the table, the first thing we'll notice is that when we look at the depth is going down each time by an amount of 5 meters. So each time we're going down by 5 meters. And when we look at the pressure, each time we go down by 5 meters, the pressure is going up by 50 meters. Now when we take that information from our table and we look at the graph, we can see that all of the values on the table make points on the graph. So 0 and 0, 5 and 50, or sorry, 5 and 50, 10 and 100, 100, or sorry, 10 and then 150, 20 and 200. And all of these points are forming a line, and that's why we have this red line here. So each of the points in our graph, or in our table, can be put on a graph, and they look like they form a straight line. In fact, that's what the word linear means. When you graph the relationship, it should always form a straight line. So what pattern do we see in the table and in the graph? Well, we can say as the depth goes down by 5 meters, the pressure goes up by 50 kilopascals. Now that's just the measurement for pressure, kilopascals. So we're able to say that this is the relationship. As the depth goes up by 5 meters, the pressure goes up by 50 kilopascals. So what do these patterns tell you about the relationship between the depth and the pressure? Well, what we want to do now is we want to look at this and figure this out to the smallest scale. And this will help us later on to get a more accurate equation. We could use this 50 and 5 to get the same type of equation. But this here, we can figure it out. Since we know that 5 meters equals 50 kilopascals, and we divide them both, 5 divided by 5 equals 1, and 50 divided by 5 equals 10, we can say the same relationship that we had over here is true, but rather than saying when this goes up by 5 meters, the pressure goes up by 50 kilopascals, we can change that around. And we can now say that as the depth increases by 1 meter, the pressure increases by 10 kilopascals. So we can say that this here is the direct relationship. As the depth increases by 1 meter, the pressure increases by 10 kilopascals. Now, let's look at the investigate section. Right here, it tells us a local phone company offers a cell phone plan that has a fixed cost per month and a cost related to the number of text messages sent. The fixed cost is $20, and each message sent costs 10 cents. Represent this relationship between the total cost and the number of text messages sent as many ways as you can. Okay, great. So now we're going to do this by first creating the two different types that we have up top. First, we had a table of values, and then that table of values had a graph. So we're going to make both of those over here now. So first, let's start with our table of values. And first, we'll draw our table like this. We'll go 0. Then we'll say 10. 20, and 30. So if we let C be the total cost and we let N be the number of text messages. Now we have defined our variables, and we can say that this is N for the number of text messages, and this would be C for our total cost. And I know that when I send 0 text messages, it's going to cost me $20. If I were to send 10, well, if I were to send 10 text messages at 10 cents a piece, it's going to be $1 for 10 texts. So this is going to be going up by 21. This would be going to 22. And this would be going to $23. So now I have a table of values. And now that I have this table of values, I can now turn that into a graph. So I'm going to draw a quick graph. And here I'm going to say this here is number of texts. And going up this way, I can say that this here is going to be the cost. And here, I'll say that we have 20, 21, 22, 23, and then here we'll have 10, 20, 30, and now we can plot those points. And those points form a line. So now we've represented this situation here using multiple ways. So far we've used a table of values, and we've used a graph. The other way that we can represent this now would be to figure out an equation. So if we want to create an equation for this situation, we can do that by looking at this table of values or at the graph. But first, let's just look at the table of values. So with this table of values, when we look at the number of text messages, every time this goes up by 10, we can see that this here is going up by 1. So there's two things we look for every time we want to make an equation from a table of values. The first thing we're going to look at here is what we call our rate of change in our dependent variable, which is right here. So that is going up by 1. Every time this goes up by 10. So what we can say is that that would be 10 cents for every 10 text messages. When we break that down, that would really be 10 cents per text message. So that would be 0.1 times n. However, what we also need to look for is our initial value. So right here, because our value for n is 0, our initial value, initial value, is 20. That means that our equation has to have plus 20 on here. So we know the total cost, C, is going to equal 0.1 times the number of text messages plus 20. Now, finally, the fourth way that we can describe this situation would be in words. So we can just say in words that as the number of texts increases by 1, the cost increases by 0.1 times the number of text messages plus $20. So we have this here in 4 different ways. First way we described this situation was we described it using a table of values. From that table of values, we created a graph that has a straight line, well, or as straight as I could draw it freehand. Then from that graph, we created an equation, and then we describe the situation in words. As the number of text messages increases by 1, the cost increases by 0.1 times the number of text messages plus $20. All right. So now let's move on to the next page here. So that was page 164. Now on page 165, we have the connect section. This is the first 4 rectangles in a pattern are shown below. The pattern continues. Each small square has one side length of 1 centimeter. So each of these inside the grid is considered 1 centimeter. So in other words, they're saying that the length of this side right here is 1 centimeter. The perimeter of a rectangle is related to the rectangle number. So as an example, rectangle 1, rectangle 2, rectangle 3, rectangle 4. We can use words, a table, a graph, and an equation to represent this relationship. Each representation tells us about the relationship between the rectangle number and its perimeter. So what we can tell is that if each of these sides here is 1 centimeter, and this was 1, 2, 3, 4, 5, 6. This one here should be 6 centimeters. What we've added in here is another 1, 2. So this just increased by 2, and it went up to 8 centimeters. This one here increased by another 2 and would be 10 centimeters. And then another 2 here, which would give us 12 centimeters. So here we have that turned into a table of, or first we have it in words. Rectangle 1 has a perimeter of 6 centimeters. Then, as the rectangle number increases by 1, its perimeter increases by 2. 6, 8, 10, 12. What we did was we looked for what was new. And what was new each time is there was a new section added to the middle. Now we look at our table. And here it's saying that in the table, the number of rectangles is increasing by 1 each time. 1, 1, 1. So it's going 1, 2, 3, 4. Here, as the rectangle number increases by 1, the perimeter increases by 2. 6, and then 8, and then 10, and then 12. And here we can look at this. They've already given us the equation that we need. It's going to be 4 and 2 plus 4. So here we have 2 times the rectangle number. Notice how this here is the rectangle number for 1, for 2, for 3, and 4. This is increasing by 2 each time, which is where we get this value right here from in our equation. The number we multiply the rectangle number by is what we call the rate of change. Now, the way we found out how to add this plus 4 to the equation is we would have to take the table back to a state of 0. So if this was to go back to 0 right here, what value would this have? And if that's the case, we have 6. The value of 6. And since it's going down by 2 each time, that would leave us with 4. That is why we're adding the plus 4. This value of 4 is what we call the initial value. That's how we can use our table to create our equation. So now that we look at the graph, in a graph, the graph also shows the pattern. After the first point, each point on the graph is 1 unit right and 2 units up from the preceding. If we place a transparent ruler on the points, you will see that they lie on a straight line. But we do not join the points because the data are discrete. What that means is that each of these individual points that we have right here is its own piece of information and are not connected to the others. So we do not join them in a straight line. I'll do a little bit more discussion on what discrete means a little later on in the lesson. So now we move on to the equation. So in equation form, we can say that for rectangle n, the perimeter will be 2n plus 4, which was the same equation that we wrote up above here, or that we said it would be up here. We said it was going to be 2 times the number times n plus 4, and we have it right here, 2n plus 4. So the equation is P equals 2n plus 4. The equation tells us that we can calculate the perimeter for any rectangle in the pattern by multiplying the rectangle number, then adding 4. The value of the P depends on the value of n. That is why we say that P is the dependent variable and we plot it on the vertical axis. That's what we know is better known as the y-axis. The independent variable n is plotted on the horizontal axis, which we would call the x-axis. When two variables are related, we have a relation, which brings us to this definition that we have right here. This definition right here is important. Linear relation. That's what this whole unit is about, and here it is defined for us. A linear relation is when a graph of a relation is a straight line. We have a linear relation. In a linear relation, a constant changes in one quantity produces a constant change in a related quantity. What that means is that as x is increasing here by 1, 2, 3, 4, this here is a constant quantity that's increasing because it's going up by 1 each time. It's saying that it's also going to cause y to increase or decrease at a constant quantity. And here we can see it's going up by 3 each time. So in the relationship above, a constant changes of 1 in n produced a constant change in 2 centimeters in P. Here is an equation of a linear relationship. Y equals 3x take away 5. X is the independent variable and is plotted on the horizontal axis. So here's x. This is your horizontal axis going sideways this way. Horizontal means sideways. Y is the dependent variable, and it is plotted on the vertical axis. Vertical means up and down, and there's y, and this is our y-axis going up and down. Here are a table of value, a table and a graph that represent the equation. So as I've just stated, in our table, our x value increases by 1 each time, and our y value increases by 3 each time. Notice that when x is equal to 0, y is equal to -5. That is why in our equation, that value is take away 5. Because that is the initial value. When x is 0, y is -5. That's our initial value, and that's how we get that from our equation. Also, we can see that our y value increases by +3 each time. This is what we call our rate of change, and that is where we get this value in the equation, 3 times x. We get that from our rate of change. We should also notice here a couple of things. First, when we look at our table, when we look at our graph right here, there's a couple of points we want to take note of on this graph. First off is right here. This point here is on the y-axis at -5. -5, which happens to also be this part of our equation right here. Also, if you notice, we have an increase to the right of 1 and then an increase up of 3. That gives us a fraction of 3 over 1. This is what we call our rise over our run. 3 over 1, 3 divided by 1 is just equal to 3. And that is where we get the value of 3 times x from. So you can see that if we have a table of values, or if we have a graph, we can use the information in the graph or the table of values to create an equation, or vice versa. So when x increases by 1, y increases by 3. This is shown in the table and on the graph. Since the points lie on a straight line, the equation y equals 3x take away 5 represents a linear relation. Remember, straight line means linear. Linear means a straight path or a straight line. Since we are not told that the data are discrete, we join the points with a line. So now we're going to go through a couple of examples. The first example is a table of values shows the cost of renting a DVD at an online store. Well, we can tell that this must be an old book because people don't rent DVDs very often these days. But here we have our table of values. So it says graph the table of values. Does it make sense to join the points? Okay, so this is where we can talk a little bit about discrete data. In this situation here for A, we have our number of DVDs is increasing by 1, 1, 2, 3, 4, 5, and our cost is going from $3.57 to $10.50 and so on. So when we want to make this a graph, we just have to take the value of our x. So I'm going to point this here and make sure that this is known as the x side of our graph, and this would be the y side of our graph. We're using the variables d for x and c for y instead. That's why the table is labeled d on this axis and c on this axis. Now that we have our table and we know what our values are, we can see that by going up by 1, DVDs are going up 1, 2, 3, the cost is going up this way, and we have, there would be $3.50 right there with 1, and then we're going up to $7, and then we're going all the way up to $10.50. So we're showing an increase of $3.50 each time. So the number of DVDs rented is a whole number. We cannot rent 1.5 DVDs or any other fractional number of DVDs, so it does not make sense to join the points. This is what we mean by discrete data. So remember further up up here, we talked about, it asked about joining points, and it says, since we are not told that the data is discrete. In this situation here, that is what the word discrete means. It means that you cannot break it into pieces. And here, since it says we cannot rent 1.5 DVDs, you can't rent a half of a DVD, that means that this data is what we call discrete. And when it is discrete, we do not join it with a line. We do not join with a line when the data is discrete. So we will not draw a line connecting these points. So B then asks us, is the relationship linear? Justify your answer. Well, even though we cannot draw a straight line to connect the dots, we can tell that it would form a straight line because each point is exactly over 1 and then up 3.5. So this ratio that we have right here of going up 3.5 and then going over 1, what we call the rise over the run, is constant the whole way up. It's the same for these 2 points right here. It's the same when we have these 2 points right here. So because we're going up at a constant rate, we can say that this is definitely a linear relation. So as it says here, the points on the graph lie on a straight line, so the relationship is linear. And then finally, C, use the table to describe the pattern in rental costs. How is the pattern shown in the graph? So as the number of DVDs rented increases by 1, the rental cost increases by 350. Each point on the graph is 1 unit right and 3.5 units up from the previous point. The pattern of increases in the table produces a graph that is a straight line. So that is how we know that is how we describe the pattern that we see both in the table and the graph. So now example number 2. So they're showing 2 different methods, and although we'll just be going over this one today, in a later lesson we will learn how to use a spreadsheet, which shows over here in method number 2. So method number 2 will be covered on another day. So here for method number 1, or I should say for question number 2, method number 1 is asking, a relationship has an equation, y equals 6 take away 3x. So when we see y equals 6 take away 3x, really what that means is that we can rewrite that. We can rewrite that just in a different way, which would be y equals negative 3x plus 6. So all I did there was I just changed the order that we have them in there. Either way, whether you have it written this way or you have it written this way, it's still the same. So A asks us, create a table of values for the relationship of 4 values for x from -3 to +3. And then B says, graph the relation. Does it make sense to join the points on the graph? Explain. So as we look right here, we have our table of values, which is going from -3, -2, -1, 0, 1, 2, 3. So each of these values here is going up by 1 each time, plus 1 each time. So they're going up by 1 each time. And we can look here in our values for y. Now in our values for y, This is going down by 3 each time. So because this is going down by 3 each time, this is how we're getting that relationship of -3 up here. So we have our table of values. Then we have this table of values, and we take each point, -3 and 15. So this is where -3 is. It's plotted up to point 15. So over -3, up 15. And all of these points, all 7 of these points are plotted here on this graph. And you can see they clearly form a straight line. And it says, since the data are not discrete, join the points to form a line. Now, let's look at how we got the values for this table. What we did was we started with our equation. We have 6 take away 3x. If we substitute x for -3, or -3 in for x, we have -3 times -3, which gives us a +9. So 6 plus 9 gave us 15. And that's where this first value of 15 came in right here. When we started with -2 for x, we get +6 plus 6 is 12, and so on and so forth. So we do this for each value all the way down until we fill this table of values out. Once we have our table of values filled out, we can then plot each point. C, if we scroll back up here, then asks us, what patterns are in the graph, and how do these patterns relate to the table of values? On the graph, to get from one point to the next, move 1 unit right and 3 units down. In the table, when x increases by 1, y decreases by 3. The relation is linear because its graph is a straight line. All right. So now let's go on to this example here, this final example right here. And this example says, well, this is example 3, solving problems using a linear relation. The student council is planning to hold a dance. The profit in dollars is 4 times the number of students who attend minus 200 for the cost of the music. That means the students need to pay $200 for the music, but it's going to be 4 times that. So it's going to be 4 times the number of students. So write an equation that relates the profit to the number of students who attend. So A says profit in dollars is going to equal 4 times the number of students who attend minus 200. Choose variables to represent the numbers that change. So in this case, we're going to let n represent the number of students who attend. And we're going to let P represent profit in dollars. An equation is P equals 4n take away 200. So now that we have our equation, we can then move on to part B. We can create a table of values for this relation. So in this case, if we assume that we're going to have either 0, 50, 100 students, so if we start increasing the student population at the dance by 50 each time, we are able to see that we have this table of values. And from this table of values, we can see n is increasing by 50 each time, while our profit goes from minus 200 to 0 to plus 200. So this is going up by plus 200 each time, isn't it? So now part C says graph the data in the table. Does it make sense to join the points and explain? So here we have plotted the points. So we have -200 when 0 people attend, We have $0 if we get at least 50 people to attend, and then we're making we're making a $100 profit if 200 people attend. So, a straight line verifies that the points lie on a straight line. Some values between the plotted points are permanent, but not others. For example, there could be 82 students, however, attending the dance, but there cannot be 82.5. Some points are not joined. So what that means is that this data here, because we cannot join all the points, because you cannot have 82.5 people, this data is, what we said, discrete. So we do not join the points with a line. Finally, we have part D. How many students have to attend to make a profit? Well, when P is negative, a loss is made. When P is 0, then N is 50, and a profit is 0. So P has to be greater than 0, and N has to be greater than 50, and there is profit. So 51 or more students have to attend before profit can be made. So basically what that's saying is that in order for these students to even make $1 off of it, 51 people need to attend. If 50 people attend, they break even, they make $0. And if less than 50 people attend, they don't make any money at all. Okay. So, now that we've covered these examples, I hope that helped out. And I will be coming back with another video explaining the questions from this section a little later on. Thank you very much, and I hope this was helpful.